I've been reading about the different subjects, and usually I've been feeling smarter and smarter as I read. But this one, I just felt that I understood less and less the more I read. So I'm going to lean back and finally understand what European Spallation source is, and Alan Weeks are going to take us right through it. Thank you, welcome.
Thank you very much. It's good to be here. Happy to be here at Medicon Village again. Our offices are across the street, so I'm quite at home here, which as a speaker makes me feel comfortable. It's nice to see you here. I also see some faces that I recognize. I am going to tell you a bit about the European Spallation source. Maybe not exactly directly how it will change humanity, but how it will certainly impact our lives in the future, but particularly how it's going to look, how it's going to be built, the things that are expected of it, and why is it being built in the first place. So I will explain a bit about that. My name's Alan Weeks. I'm responsible for not only the communications and the external relations, but also the way we manage the collaboration at ESS through our different collaborating partners, which I'll talk about as well, because ESS is a quite collaborative project. It's being built by a lot of scientists around Europe, different institutions, and it's really one of the largest research projects being built in Europe today. But it started like this. This is in May of 2014. There's a green field just to the outside of Lund here, and some of you may have actually visited nearby there the other day, because we had a very important event here in Sweden with the opening of the National Synchrotron Max 4. So we're actually the next door neighbors, or will be when we're finished. And it's very important that those two facilities are close together. But what you see then is a green and somewhat brown field with yellow areas as well. That's important because it means really this facility is being built from the bottom up. It's being built from scratch here. Very often when a new research instrument like ESS is being built, it's located in an area where there is already an infrastructure in place. Maybe there's already a large facility that has built similar type of facilities like this. So that presents a certain challenge to creating a greenfield project in a place like ESS. One of the challenges is to actually visualize what is it going to look like in the future. So just to kind of get a sense of what it looks like, I've put together some images of what we're working towards, the goal, and then I'll show you some pictures of where we are today, and then we'll talk a little bit about what ESS is going to do and who are the people that are actually building ESS. But if you were in a helicopter, or nowadays in a drone, flying over ESS in about 8 or 9 years from now, this is kind of what you would see. You would look down on what we call our target building, where Spallation and many of the instruments are placed. And then if you were walking along the campus early in the morning or late in the afternoon, in this case, I guess, you would start to see the target building from a different angle. And you get a sense that it's a quite large facility. This whole space takes up about 75 hectares. And then what you see coming in front of us from the accelerator there, or from the target building, is what we call our linear accelerator. So this kind of grass-covered, long 600-meter tunnel, where we have a large particle accelerator. If you're driving along the highway, this is what you'd see. You can see kind of moat-looking things down there, ditches almost. That's because we don't have fences. When you look from the highway, or you look from the road, we want it to be a clean look, and we want it to be an open space that people feel is a part of their community. So this is a sense of where we're building it. You see we have a large accelerator tunnel. We have several support buildings around that, all leading up to the target station. And then just beyond the target station, at the very end, you will see where we actually have the scientific instruments, which I'll talk about as well today. So this kind of gives you a sense of the facility, what we're aiming towards, but I showed you a little while ago, this would be the final product of that green field. We're not there yet. We have a lot of work to do before we actually get to this stage, and so it's in a process right now of actually being built. So let's move on and see what it will actually look like when it's finished. This is what it looks like when it's finished. Let's see what it looks like now, I should say. Okay. So first of all, what is ESS? So some people often refer to it as a kind of a microscope, and let me explain why. It's not really a microscope, but it does look at things at a very small scale. It's a tool, a research tool that enables us to see things at a molecular level. It's not only something that enables us to see things at a molecular level, it's a tool that allows us to see through things. Just like Superman had X-ray vision and could see through things, with the tool that we use, which is the particle, the neutron, we're able to penetrate into different matter and then actually make observations of that matter. So for example, This is a case of a coffee pot in situ, and obviously you see there's coffee inside there. Now, the nice thing about this is you can penetrate through these materials the same way that you could do with a synchrotron, with X-rays like an ESS, but because we use neutrons instead of X-rays, you can penetrate and see matter in a different way. And in particular, with neutrons, we're able to see hydrogen, which is a very light element in a very small atom. And the neutrons interact very well with it. This enables us to see things like liquids, soft matter, things that are relevant for life sciences and medicines and tissue, things that X-rays don't see well. It's even better if you have those two things together in the same place, like we do here in Loom, because then you can use both tools to understand better what matter looks like at the very basic level and inside matter. Now, one other nice thing about neutrons is because they're charge neutral, they're called neutrons, that means they can penetrate very deeply into things like metal. So you can actually see not only through metals, but you can see into metal and see also the densities of metals. So this helps us to observe different materials. And I'll talk about some applications of why that's important. Now, our facility is called a spallation source, because what spallation means is you break something up. Literally, it's a mining term, to break up rocks into small pieces. So what we do is we break up the rocks, so to say. We break up the element that we're using, tungsten, using protons, and you'll see a video of this in just a moment. And when we do that, it gives off neutrons. And these neutrons are actually the source of the different material that we use. So we take protons, accelerate them almost to the speed of light, so 98% of the speed of light. That requires a lot of energy to be able to do that. And then that means that the accelerator is hitting this target building with a force of about 5 megawatts. So that's like a Volvo hitting into a brick wall at 60 kilometers an hour, about 14 times a second. That gives you a sense of the energy that's being released. And that spinning wheel there is made up of solid tungsten or wolfram, a very dense, hard material. And as this proton beam hits it, it breaks the material up, and it's going through these kind of guides that you'll see in just a moment. You can actually take neutrons and guide them out to a certain place. And then once this neutron comes out, you'll see that in a minute, then you can actually do the experiment you're trying to do. Now, this requires a lot of shielding because it's a lot of energy, a lot of heat is generated when you're doing that. And then you also have to have a way to be able to cool that system off. So we have a large system that we call our cryogenic cooling system, and we use liquid helium to be able to cool down this very hot temperature. And also it's part of the reason why this target wheel rotates, so that the heat can be dissipated as it absorbs all the energy from that target. So coming out off of this target, you'll start to see these scientific instruments. So we have planned right now to build about 22 different kind of instruments to be able to see these neutrons or use these neutrons to see matter. Eventually we could even build more than 22 instruments. Each of these instruments, just to give you a sense of the scale, cost on the order of 10 to 20 million euro a piece. And they're designed by some of the world's experts, each one in their own discipline, for using these neutrons. So it's a quite large project. We plan to build 16 in the construction project. So between now and 2023, we'll build 16 of these instruments to go along with this facility to start doing research. Now, the way that this actually works, we saw a little while ago this proton going through. When the neutron is coming off the target, then you have to kind of understand that there are a number of neutrons coming off, and we want to pick out some of the ones that are at just the right energy levels, just the right wavelength, so we have to kind of filter them out. As they go out and they hit the target, they will interact with the material that's there inside that target. And it's a different kind of interaction depending on what that material is. And that sends out a signal that we can then detect. And then based on what the material is, we know what kind of material is inside there because we have a record. We can understand based on spectroscopy or different applied methods how to actually explain the material and the structure of the material. So this beam of neutrons comes through, we chop it up into pieces, okay, and then as it hits a sample, you might see that it could bounce off of the sample, like in this case, and diffract up into the detectors behind there. And there's a large bank of these detectors, so they could take up anywhere from 2 to 3 square meters of space in which they're detecting in a time-of-flight kind of methodology what these different materials are. So this is the way we see things. It's not the same way you see things with a microscope, but it does allow you in the same way to see things at a very small scale and also to characterize what kind of material is actually in the sample that you're looking at. Now, like with a microscope or like with a camera, if you've ever taken pictures with a camera, you'll know that it's important to have a certain amount of light to be able to take a very clear picture. If you don't have light, you get a dark spot, yeah? And so the amount of light is equivalent to the amount of photons when you're using a camera, or if a microscope is your choice, then you have to have a lot of light to look down at very, very small levels. It's a similar thing with neutron sources, which neutrons are not as abundant as photons. There's not as many of them, and they're hard to make, and they're very expensive to make. And so if you can have a very bright source, then that allows you to see things at a very smaller scale, and it also allows you to not leave your camera open as long, so you can do experiments faster when you have. What you see here is a table of different kinds of neutron sources over the years, starting back in the 1930s when we first discovered the neutron and started to use it as a way to explore matter. And then when you see that kind of orange scope there, or line there, that gives you a sense of what is the most traditional form of source of neutrons, and that's a nuclear reactor. And now nuclear reactors today are not really favored in terms of building either for energy or for research. They're very expensive to build. They require certain safety requirements to be able to construct them and operate them safely. And what you also see from this line is that at a certain point in time, based on the physics, the reactors were only able to give out so many neutrons, and then we hit kind of a ceiling. They couldn't get any brighter than that. So the only thing we could do was focus on how to make detectors that could detect the neutrons better. Then back in the 70s, and then especially when we moved into the 80s, some really smart people in the UK at a place called ISIS at the Rutherford Appleton Laboratory there, they came up with a working user-based facility based on spallation, using an accelerator to be able to generate these neutrons. Now that's really nice because with an accelerator, you can turn it off if there's a problem. So that's useful. But in addition to being able to switch it off, it also can create a very, very bright peak in terms of like a flash bulb on a camera. So then you can take this picture with a much brighter source of neutrons than we were able to do with the reactors before. What does that mean? That means now we can look at things we couldn't look at before. We can do experiments that we couldn't do before. And what you see here is a logarithmic scale. So obviously this is a little bit tricky for the eyes. We're not really looking at a kind of a linear scale here. When you see things like the ISIS and the blue line there, and then the North American facility, the Spallation neutron source, SNS, JPARC in Japan, and then eventually ESS, what you're seeing is these are orders of magnitude brighter. So it's much, much brighter than the ones before it. So it's a big step forward. And for the scientists who are chemists, who are material scientists, who study things like biology, this is really, really important because this opens up a whole new range of possibilities for experiments that they can do. So what do they do? What kind of things do they do? Well, before we get into that, I just tell you a little bit about this process of ESS and how long it's taken to actually build ESS. The idea of ESS started almost 20 years ago. There was a study way back in the 90s that said basically this kind of source, a non-reactor spallation-based source, would be important to have not only here in Europe, but also in North America and in Asia. And at that time, Europe has really been the leader in this particular field of science, using neutrons for material science. And so the plan originated really to build this facility here in Europe. But as things turned out, it took much longer to get that plan off the ground. There was a plan to build it in Germany. That didn't really get traction at a certain point back in the early 2000s. And at that point already, here in Scandinavia, particularly in Sweden, and particularly locally even here, there was an interest already to say, well, maybe this is a project that would fit here. We have already a long experience working with synchrotrons. Maybe this is something that we could get here in Lund that would be very interesting to complement our plans to build a synchrotron in the future. And so there were already, as far back as 2003, interest here in Sweden to begin looking into getting the European spallation source built here. Now, at that time, Germany had an original plan, decided they wouldn't do it. And there was, many of you will remember who are from around here, there was a campaign to actually, in fact, a competition to get ESS here. There was a competition with Spain and with Hungary, where there was also a great interest to have this project here. And so Scandinavia was successful. Together with the Danes, came up with a fantastic proposal and a very serious commitment to the project, so it was decided to be put here. And then back in 2012, we took that original design and we updated it so that we could start working on this latest design. And the construction started back in 2014. So we're really just now about 2 years, coming up on 2 years into the construction. And we expect already to start to generate some of the first neutrons in 2019, and then actually start the user program to do the research in 2023. But we'll continue to build instruments. We'll continue to build instruments beyond 2025 even, but the construction should end there. So it's a long project, it's a big project, and it's really a European project. And I'll talk about that in a moment. You'll see a bit more how much of a European project it is. So the host countries, Sweden and Denmark, are obviously making a huge commitment because they're paying for almost half of the construction of this project. So 47.5%, almost all in cash. So much of the construction that you see being built out on the site today, when I show you some of the pictures there, you'll see that that's actually being built through the funding here in Sweden and Denmark. But also there are other countries, the non-host countries, that are contributing to ESS, both through cash, but also through in-kind deliverables. Now that's an important aspect for us, because when you start up a greenfield facility, and I showed you that empty field before, well, we originally started off with a very small group of people. Today, that's grown. But attracting experts from around the world who are really the experts in this particular field is not easy. And many of the laboratories around Europe have expertise already in this field. For example, the British laboratory that I talked about earlier, some of the German and French laboratories. So it makes sense to bring that expertise together and focus it on a single project rather than building multiple facilities around Europe. So that's why we see this partnership. Today, we have all of these countries, so it's actually 12 member states, and then we have a number of observer countries that are also planning to join. I have to make a special point because it's an interesting contrast today. You know, there's a very important vote going on in the UK, who is, as of a week and a half ago, a member of ESS. So you see that even though there are some trends to move out of Europe, in this case, science is bringing the UK into ESS, and we are very happy to have that collaboration anchored well in our project. Now, if we look at the life cycle of the project, and you look at the overall lifetime of the project, we have this 1843, that square represents the construction cost. How much does it cost to build ESS? But the plan is to operate ESS out until at least 2065. So it's a long lifetime. So even after it's built, we're planning at least 40 years of operations. So, and that's a significant investment as well. And if you remember, when we showed you this graph, while there's a huge investment from the host countries in the construction period, there's also a huge investment from the other countries during the operation period. And that's fantastic, especially for those here in the region, because that's really investment that comes into the region and benefits the community, and benefits industry, and benefits the people who are living here. So, go out, and there's even plans at some point we'll have to actually take this thing apart. And we have to know now and start planning now for how it's going to be taken apart. Now, in 2014, just after we kicked off this ceremony, we said, well, it's important to send a signal out to our community of stakeholders that this project is getting going and it's ready to go. There was a long history already. And so we invited over 700 people here to Lund to join together at the official kickoff, what we call the foundation stone ceremony for ESS. And just about a month after that, month and a half after that, we then started to pour the first concrete. So obviously things started moving very, very quickly. We had the site excavated. We did an archaeological excavation out on the site before we started digging. We found some interesting findings there as well. And since that time, if you look now on our website, essass.se, there are 4 webcams that you can go to 24 hours a day, and they're updated every 10 minutes. I took this picture about an hour ago. And this is more or less what it looks like out on the site today. And if you look at it here, this is almost as if you're standing closer towards Lund and closer towards Max 4, and you're looking at the target building. That big hole is where that big target building will be, that round roof building. And then looking down in that direction towards the top of the screen is the long 600-meter linear accelerator. And then over to the left, you can see some of the support buildings where we have, for example, the cryogenic systems and what we call the Klystron Hall, where we have all the power supplies that are running the facility. And then over to the left side of the screen, you see some things sticking out of the ground. Those are called pilings, and there are 6,000 of them out on the site, concrete pilings. And what they do is they ensure that the facility is on a stable base, that things don't move. Well, that's really important when you're a scientist, because you want to know that the signal that you're getting, that beam that you're getting, is really going to be in the right place and things aren't moving around a lot. It has to be a very stable facility. So this took a lot of pile driving, and that solid concrete base there for the target is really a significant construction effort. It's a massive construction that's going on there. And then if you kind of were flying from a drone, again, you can see some of the pilings there. This is from about 3 months ago, maybe a little bit sooner, 4 months ago. You could see from the top view the way the construction looks. The target hole is not quite dug yet, and you can still see the accelerator tunnel, which has not yet been covered up. And so that's a sense of what it looks like today, relative to that video that I showed you earlier. Yeah? And it's a quite, as I said, large space, so you should come visit us and have a look at the construction site. So over here we have our construction buildings. Today we have a team of people both working at the site and here in Medicon Village. We have our offices where most of our technical organization is based, and we will start to move out onto the site later this year and early next year over a period of time. It will take us probably about 2 to 3 years to really move out to the site. Okay, so you have a sense of what ESS will look like in the future, as well as kind of what it looks like today. So why do we need ESS, or why do we think we need ESS? Well, you may not specifically and individually feel like you need ESS. It may not feel like you have a direct impact on your life. But I can tell you, there's been a lot of discussion about ESS over the years. And a lot of people have debated about whether or not they're willing to put almost 2 billion euro into an investment like that. As you saw earlier, we have now almost 15 countries. There are 12 who've already joined and committed to join, and then others who are considering joining. So if you can just imagine, if you've ever had to sit down in your department or in your organization and negotiate a budget with your colleagues, how complicated that can be sometimes. And then you put 15 countries together and say, well, we'd like you to contribute this and this. And then the contribution is not only how much money will you give, but what technically will you do to actually build this facility? What instrument will you build? So it's a very complex process. But I will say, we have an advantage that this has been recognized already some time back as a leading project on what's called the S3 roadmap, which means it's really one of the most high-profile and unique projects in Europe today. And if you look across a map of about 50 different projects that are in Europe today, ESS is really at the top in terms of the overall value of the project and in terms of the strategic importance to keep Europe in the lead relative to this kind of science that we do with neutrons and this material science, because it has a very important impact strategically for Europe's industry and for the way that our society benefits from newfound materials. So it's been identified as a project that's very, very important. And just to kind of give you a sense of some of the things, just a very, very, very small sampling of some kind of impacting things that impact on our lives every day. So biofuels, this is something you must read about or have heard about. And one thing, for example, that's very interesting in Sweden is how could you take the massive timber industry you have and take all this wood and timber pulp that you have and convert that into biomass, and particularly into liquid fuels. And it's actually very difficult to take cellulose and break it down. It's not very cheap to do it, it's expensive, and you have to understand on a very basic molecular level, how can we efficiently break down a molecule to be able to convert that molecule over to a biofuel? Well, neutrons provide an incredibly good tool for being able to look at hydrocarbons, because I already told you, neutrons are very good at being able to identify very light elements, particularly things like carbon. This was a study that was done at the ILL, which is the leading facility today for neutron research, in which they studied the ways that cellulose can break down in an ammonia solution. And that's very important because they're able to actually look and see how it starts to break down. And when you understand how it starts to convert, then you can design processes to be able to create fuels more efficiently. So that can have a direct impact on our economies, obviously, as well as it enables us to have some kind of sustainable fuels. This is very, I would say, bread and butter type of research for neutron facilities. These are the kind of things that have direct impact. It's very much everyday life kind of research. We look, for example, at a case like this one. Again, these are all studies that were done at other labs because we don't do research at ESS today. But this particular company, Evonik Industries, they wanted to understand a specific catalyst that was used to manufacture vitamins. This is a generic vitamin manufacturing company. And they thought, well, if they had a certain idea of how a certain catalyst worked, then they could improve their manufacturing capability, which would give them a competitive margin, which would make them a competitive company. So they were able to use neutron scattering to understand exactly what happens on the surface of a catalyst during a chemical reaction. That was then information that was their information. They took that into their own processes, and they were able to develop a manufacturing process for vitamins that made them very competitive on the market. So it's, again, a very concrete example of how this science can apply in a business situation or to our everyday lives. So Airbus has worked with ISIS for many years, analyzing, for example, things like the welds that they use to build the A380. So as they're using composites, as they're using new kinds of aluminum welds and materials, things like that, when you're doing a weld as a machinist, you're not always sure how successful that weld is. And you can't really just take your glasses or your microscope and look inside there and see how good the quality of the weld is. But we said before, we're able to penetrate metals also to varying degrees. You can actually look into a weld and see the quality of the weld. You can see, are there air bubbles inside there? Another nice thing about using neutrons is you can look at things besides just metals and welds. You can look at composites. How are composites laminating well together? So the Airbus 380s contain a lot of composite, epoxy-based laminates, things that are very difficult sometimes to examine on a very quality type of level that you would want in an airplane like that carrying hundreds of passengers. So they're able to understand the manufacturing process, the welding process, the laminating process, and then take that into their factories and apply it. And it's facilities like ISIS and in the future ESS that enable them to have a very good understanding of that in a kind of scientific and qualitative way. These particles up in the atmosphere attach to each other to create pollution. So what we can do again is in a certain controlled environment like this experiment, beam lines and experimental stations we can simulate and create similar conditions like we see in the atmosphere on our everyday life, and we can actually observe how different molecules are bonding together, and that makes us understand better, particularly how, in this case, vehicle oil can create a polluted situation relative to ozone, and how we could possibly slow down cloud growth. Aerosols form and they mix with raindrops, but we don't really understand the ways they do that. So these kind of research, watching again very light element type of liquid things, waters, gases that contain hydrogen, this is where neutrons are particularly good. New food formulations. And then I just wanted to use this example to make a point that, so all that's fantastic. And then you probably remember that I said the research doesn't actually get going until 2023. And here we are today in 2016. So that's 7 years from now. It's a long time. So I just want to point out that actually also in the construction of large facilities like this, we push the technology to the state of the art. We're really trying to do things that have never been done before, and that forces us to create new instruments, new electronics, new devices, and when we do that, we don't just sit in labs and come up with these ideas. We work together with industry to formulate these ideas, because oftentimes a researcher in a lab can come up with the idea, but it really takes experts in industry to understand how to manufacture that idea, how to create that idea in a practical way that you can apply in large volumes or have a reliability factor and a quality factor that you really need. So what we see is, we've particularly seen this with ESS, but also with MAX 4. You saw really a lot of technology that went into the construction of the facility that enables not only industry, but other facilities around the world and companies to benefit from that during the construction period. So how do we do ESS? So this is kind of my home stretch now. I know it's late in the afternoon and it's warm outside, and I hope you had a coffee before you listened to me. Basically, the way that we look at the project is, at the beginning it was an idea, it was a campaign, and then it became a kind of a commitment, and then we had this design, and particularly Sweden and Denmark were able to make a commitment to the project. It's now a project, so it's in a construction phase, and then it will become a facility that actually operates and actually does and performs the science that we've been talking about. So when we get to that stage, you see these are the kind of commitments that countries have made to this project. And these are the kind of, let's say, commitments that required convincing, but it's also the level of understanding of the importance of the project, I think it signals. Right now, ESS has about a 99% support in terms of funding. Now, it's actually more on the order of about 97% because some of this was investment that happened before the project actually got off the ground. But the important point here is we have a number of partners and members who are already in ESS, others who are joining it, so there is a great support and recognition for the need to be able to have these kind of tools in the world, and particularly this one here in Lund. And when that commitment was made, and I told you earlier, there's a different way to fund that. You can fund that through cash, which is a very obvious way, but then there's also this in-kind contributions that come as expert contributions from our member countries. Now, this is a very significant contribution, not only because it's a big number, it's 750 million. That 750 million represents almost all of the technical scope of our project. So it means the really expert knowledge of building ESS, most of it is being built outside of Lund and will be brought here and will be placed here and assembled and installed here in Lund. And a significant portion of that will be in the accelerator, 75% of the accelerator. The instruments, you know, it says the instruments, but it also includes all the support systems around the instruments as well. So almost all of the instruments will be built outside of Lund. The target station, although it's a big, massive concrete and steel block, it will also, much of it be built outside of Sweden and brought here by partners. And then even the computer control systems that actually make the system work, much of that will be built by partners. And so this in-kind is very basic for the way we construct the ESS. And it's, I think, basic in terms of thinking about the different people who are building ESS. Now, our staff here in Lund are about 35% women. More than 50% have a master's degree or a PhD. About 43% are from the host country, Sweden and Denmark. So then there's another 67% that come from somewhere else. Today we have about 367 people working here. What's very interesting is 47 different countries are represented in our small 400-person organization. So it's a quite diverse organization. And that's just what's happening here in Lund today. If you go outside of Lund, then there are, as I've said before, institutions all over Europe. About 100 institutions. Of those 100, nearly 50 are direct, what we call in-kind contributors, who are actually helping to build ESS. And that's a massive project in itself, just managing all those different interfaces. And then a while back, some of you will remember that we produced a video, and some of you are even in this video. But what this video is very important. We did this at our foundation stone ceremony, and I just wanted to give you a little bit of the background of this video. We asked 26 different institutions to make us a 30-second to 1-minute video saying, you know, ESS, we're happy to see you get started. Now, that sounds like a very small thing, but that's actually a pretty big thing. If you see the level of effort that these scientists took the effort to get together and make a video and send us a video because they are so excited about being a part of this project. It's really kind of a very nice feeling for us when we got the video, because many of them went to great efforts to produce it. And this was at the very beginning of the project. We just hope this enthusiasm will stay throughout the entire project. We have to work on that. But it gives you a sense also of the different people and the different places. And I think this is one of the important things about a project like this. It brings people together. It brings scientists together. It catalyzes people from all over, in this case Europe and all over the world, to really work together on a project and deliver something.
We are your fans and we are your players.
Our French colleagues. They're doing a large part of the accelerator for us.
We love to scatter neutrons.
One of our German colleagues, one of the biggest labs that we're working with, is the director of the lab.
We are glad to contribute and we wish the project all the best.
We just asked them to send us a video. They produced it on their own.
The pathway to be the technology is targeting to deliver technology and passion for ESS. We'd like to thank all of you.
That was nice. So anyway, so it's a very enthusiastic group of many, many people. It's probably about another 1,000 people around Europe that will be working on the project outside of Lund, as well as the team that we have here in Lund. And this is really one of the most interesting things, at least for me, about the construction of the project, is really how the people come together to formulate this. It's a massive collaborative effort, and it will certainly have a huge impact on Europe. So with that, I've kind of end my discussion, and I'm happy to answer any questions that you might have. And thanks for your attention. Yeah.
Thank you, Alan. Very inspiring, right? It makes me quite proud to be from this region. So many cool things. And now, followed with Rick Ashley music, I think we can take it to the next level, right? Does anyone have a question for Alan? And he has a second to answer them too. You must have, yeah, we have one here.
I have no question, but I have a comment that might be of interest, because this is about the...
Go on, give him the microphone, please. Thank you.
Not a question, but a comment, because it's about the interaction of science and society and industry. So you asked the question, why is it worth spending 2 billion on something like this? Just point out, so I come from the ISIS facility in the UK, so we have a facility like this.
He doesn't just come from there, he's the director.
We've done a recent economic impact study, so 30 years of operation, right? And it works out that even based on basically 2 or 3% of the research we do, the return on investment for the UK is about 200%. Now, that's public investment in research, right? The typical return, the good return for normally industrial investment in research is about 50%, and for public investment, 15% is good. So 200% is stratospheric. And that's based on a tiny bit of what we do. So that basically just tells you these things are really worth doing.
Absolutely.
Oh, wonderful.
Yeah, no,
I guess you agree, Alan.
No, I know it for a fact, yeah. I mean, the guys in the UK have been very, very good at really quantifying these impacts, and that's important because, many of the impacts are long-term impacts. You don't see them the next day, and so you have to kind of track them. But they've actually done longitudinal studies over time, really observed that, and I think the initial reaction was those numbers can't be right, but they've done a lot of detail to show that they really are, paying off in that kind of way.
That's wonderful. In a world where we need political support, we need numbers. I think we have, if we can be quick, we can have time for this question too.
Yeah, my question is, the background to the question is that you probably, if you look at the use you had so far, it turned out that the use was in areas where you didn't expect, maybe, some of them at least. And then my question is, how much effort do you spend on trying to predict what actually you can't predict, and I mean the future use? Well, of course it's a tricky question, but maybe you can comment.
Yeah, if I can comment on what I don't know. That's a good question, and in the sense that what do you do anyway to enable yourself to be able to take advantage of something that you're not even sure how it's going to work, what the capabilities will be. I mean, first of all, I should be very clear. We are constructing and will operate a facility that other people will actually come and do studies on. So ESS will have scientists in-house, but we mainly facilitate research for others. So professors coming from universities and from all over the world, anyone can come to ESS and submit a proposal, and it will be accepted on the basis of its scientific excellence. Now, when we think, for example, about the construction and planning for the future, we think about instruments, for example, that will have a certain capability when the machine is turned on, but we already build into it now a design path to be able to expand on that in the future, and to be able to do experiments that may be, not predictable today, but we understand from a technological point of view, we'd like to have a certain capability in the future, and we don't want to close the door when we choose certain technologies, that's for sure. We're looking, when you are planning for 2023, for example, you're already in a way planning for something that's obsolete, because by the time you get there, the technology, everything will go. So in a sense, it's a bit counterintuitive. You have to plan, but leave a lot of space open. You have to be agile in the way you think about it, which means you don't lock everything in this early on. You leave possibilities for flexibility in the planning. And then that can be tricky when you try to line that up with funding, because people like to see concrete plans for funding. So we have panels of scientists who come together and they form so-called scientific and technological panels. And what they do is they advise us on what the science could be and what the tools could be in the future. And we start thinking about that. But they're really, it's not just our team, it's really drawing in experts from all over the world who are, thinking about those kind of things on a regular basis.
Wow. Thank you. Thank you so much, Alan, for coming to share.